So it's great to be. Okay, thank you. I think I just want to make sure that we're all on the same page here, because that has never left my brain, even after being at Colby for the last 18 years. I'd like to start by telling you that no man is an island, and no man is a peninsula. And the work that I've been doing over the years is really a collaborative effort. And all of my colleagues who are listed here, I'll go through them in a minute to get some idea of who they are all responsible for helping in the story I'm going to tell you today. Because it's a long and complex story. I'll try and keep it not as long, but you know, professors like to talk and the like. So this is when collaboration, Ronald Reagan in a red state, what more could we want out of the beginning of a talk? My colleagues I've been working with for the last 15 years are Johan Neffling, Johan Neffling, who's the stratigrapher at the Council for Geoscience, which is the US GS equivalent in South Africa. I've been working with him for 15 years. Sandra Camo, who's the director of the Jack Satterley Geochronology Lab at the University of Toronto, where they established many of the techniques that are now used as standard for age determination. John Geisman, who's professor of geology and chair at the University of Texas at Dallas. And John's past president of GSA. He does all my paleomagician stuff. He's my magnetics person. Marion Bamford, a paleobotanist at Wits University in Johannesburg. Cindy Loy, who's at the University of California at Berkeley at integrative biology. Neil Tabor at Southern Methodist University, who does my stable isotope work, or our stable isotope work. Rose Previck was another paleobotanist. And I'll tell you, over the last 15 years, about 30 undergraduate research assistants that have cooperated with me in South Africa on this project. And you'll get to see a couple of them in the field. So what is the end Permian extinction? Right? We all hear about this in historical geology. It's what Doug Irwin called the mother of all extinctions, because over a period of about 60,000 years in the marine realm, we lose about 95% of all known marine biodiversity. So imagine a world today that you know, and then a couple thousand years from now, a world that's completely different because everything that you knew was gone. And this extinction event, which was first described over at the Meishan section in China, gives you an idea of the biostratigraphy, that there's an initial extinction event, and then over about 60,000 years or so, we have a pattern of other groups dropping out. And only a few of these things get left. I'll be a janitor too. I can do that. So the idea is that over the last number of years, the mechanism by which this extinction has been proposed to occur is in direct response to, to this, the large igneous province of the Siberian Traps. The Siberian Traps, if you may have taken a historical geology course and heard about, is an area of basalt that extends over a significant portion of Siberia, that almost 2.5 million square kilometers of material now exist at the surface, over 100,000 square kilometers of area, and about 2.5 miles of thickness, which is a lot of damn basalt, in about 2 million years, right? We know that we've got a high precision date. Sam Bowering and Burgess published this in a couple of years ago, where the lavas began at 252, and actually the first date at the base of those lavas, Sandra Camo published in the early 90s, and that still holds. And the last amount of puffing occurs at about 251.9. And it's estimated that the large igneous province began its intrusion phase about 300,000 years before the extinction event happened. Back. Okay, this is going to take some time. So this is a plot that Sam published a couple of years ago, which gives you an idea of when lavas were extruded over the Siberian Traps. And the dates for these are based upon 300 grains of zircons at very high resolution, a lot of dates over these. And that the extinction event, which occurs approximately here, is then followed by a number of series of intrusives in the area, some extrusives, intrusives, and then boom, it's gone. And if we take a look at this, if we can take a look at this, we can't take a look at this. I will go back to analog technology, the stick, right? Woo, analog, right? This is the Permian, this is the Triassic, and these are the dates over which these things occur. So you'll notice that about 300,000 years prior to the extinction event in the marine realm, we start to see these intrusives, these extrusives, a bunch of intrusives, and then in the Triassic we end up over here. So what did I just do with the... Oh, will this work?
Yeah,
center button. Boom. Boom.
I don't know if
You're lying to me, Chuck. You're lying to me.
the pointer works.
There it goes. Oh, the pointer. What am I, the Bahama Gifa with like 6 arms? Come on. Seriously. You got a point for me? Okay, good. So the idea is that when all hell breaks loose in the marine realm, the terrestrial realm also underwent massive extinctions. And that it's estimated that about 75% of vertebrates on land become extinct. We lose plants, the Glossopteridales, which is, you may recall from historical geology, is one of those plants that Wegener used to say all the southern hemisphere continents were the same because the same tree had fossils from South America all the way to Australia and in India. And supposedly the Glossopteris extinction occurs here, and this is paralleled by a series of excursions in the carbon record. We now know there are many more excursions than what's shown here, and that this light amount of carbon increase to about -30 ppm is a direct function of the Siberian Traps volcanics. And the idea is that as we continue to get these basaltic intrusions coming in, CO2 and methane are enhanced in the atmosphere, then there's a drawdown of some of that, not a complete drawdown. The next series of eruptions occurs, we increase the level a little more, there's drawdown, but never drawdown to the initial point. And as we continue to increase, we eventually hit a tipping point where all hell breaks loose and everybody dies, okay? Over 300,000 years. So my concern as a initial paleobotanist was one of, I don't live in the ocean, I do live on land, and if all hell breaks loose on land and the ocean at the same time, and this is a coupled response, we should understand whether or not everything on land goes to hell in a handbasket as we do in the marine realm. And I was fascinated by the idea that the late Permian becomes a drying phase. The model is such that all the Glossopteris vegetation dies out, the trees die out. We change the river system sedimentology from meandering to a low sinuosity right near the boundary, and right after the boundary that changes to a braided river system because of aridity, et cetera, et cetera, et cetera. And the model being here initially in South Africa was then extrapolated on a global basis by Mike Benton to all the other Permian Triassic sections, essentially saying that we can correlate this braided or meandering to braided fluvial event across the globe, and hence the vertebrate extinction equals the marine extinction, and we're in down a lot of trouble. Okay. So let's go to South Africa. Oh, let me go to South Africa. Okay. Now we'll go to South Africa, right? Because here we go, South Africa. This is my hat. Okay. So now we're in South Africa. We're away from the global signal. And we'll go to the Karoo Basin. The Karoo Basin, which occurs, analog, occurs through here. This is going to be one of those seminars you're never going to forget, right? Never going to forget. The main Karoo Basin is part also of the Kalahari Basin through Botswana, and actually this goes into western part of Africa and eastern part of South America. But the Karoo Basin is formed as a foreland basin in front of the Cape Fold Belt, as we had Antarctica and Australia subducting beneath South Africa, pushing up these marine rocks, which are principally early Paleozoic rocks into the Cape, and then the sediments coming off of those into a foreland basin in front of it. About in 2011, which is, geez, almost 10 years ago now, Martin de Wit came out with a different model than this standard Karoo model of continued compression and then slices of faulted rock producing the interior topography, with this idea that the rocks in the basin itself undergo these subfoldings and that the Karoo fill is actually this material that fills the foreland basin. Irregardless, we have kilometers, tens of kilometers of rock that fill this big hole in the ground. And it's an unusual hole because this is a completely continental basin. Now, if you think around the globe today and think about where rocks are being deposited, or sediments are being deposited, you think about oceanic basins. There is no ocean sediment here by the time we get to the early middle Permian. It's completely landlocked. So all the sediment that's coming off of these gigantic mountains in the Cape Fold Belt are filling a bowl, which means we have a fully continental section without marine influence over which we can determine what happened to the terrestrial realm. And that's important because we don't see a record outside of what was in that basin. Now, bingo, okay? So quickly, to run you through the geology of the Karoo Basin, we have some late Carboniferous and early Permian glacial diamictites that are overlain by turbidites. And if any of you guys ever go work for Shell, for example, they will take you to see the Eka group over here in Langsberg, which is right about here, because that has the most beautiful set of turbidites you'll ever see, and that's the models they use for their subsurface turbidite plays. By the time we get to the top of the Eka group, we transition from an open, we now know it's marine system, into fully continental rocks, and those are subdivided into a number of different formations in the Beaufort group. Now, the problem with the Beaufort group is like it's colorblind, right? You've got green siltstones, you've got reddish siltstones, and you got yellowish gray sandstones. And that's about all. So the problem was, how do we subdivide these rocks to get an understanding of where we are geologically if all the rocks look the same? This monotonous terrain. So in the early 1900s, as vertebrates were being discovered in these areas, and we got tens of thousands of vertebrate samples, the Beaufort group was subdivided based upon the vertebrate biostratigraphy. And that comes up with 8 different zones, with these lower zones being Permian, the upper zones being Triassic. But are they? The only reason we call those lower zones Permian and those upper zones Triassic was because in 1906, Robert Broom, who is an anatomist and a medical doctor, decided that, oh, I think the dicynodons are Permian, and I think the lystrosaurids are Triassic. Now, Broom is the same anatomist who was first to describe your ancestor and my ancestor out of the Steinkirk Fountain caves just outside of Johannesburg is a little skull about the size of this cup of a child called the Taung child, T-A-U-N-G. And that was our earliest hominid ancestor ever found. He's the guy who described it. So, important guy, his ideas must be right. In 1911, he goes, the Lystrosaurus zone is probably this, the Cistocephalus zones are above it. And then it catches traction. Now, one of the things that you may learn as a scientist as you go through life is that once an idea catches traction, it catches traction. Everybody likes an idea that makes sense and repeats it over and over and over and over and over and over again. And one thing that Max Planck said that I enjoy, and maybe you will enjoy too, is that science progresses one death at a time. right? So, no, seriously, right? The old ideas go out of style when the guy who promotes them dies, right? So we're going to see that today, essentially, when Lystrosaurus dies, or maybe it doesn't die, or maybe Dicynodon, maybe it doesn't die. But this progress, or at least this model, has been in the literature now for over 100 years. And the most recent iteration is by Roger Smith at the Cape Town Museum, and one of his former students in Bloemfontein, with this extinction event that occurs at the changeover from the Dicynodon zone, which is now called the Daptocephalus zone, and overlain by this Lystrosaurus zone, and in a very tightly constrained stratigraphy of about 70 meters of stratigraphic section. They believe that we have two phases of extinction, a rapid recovery phase right after the extinction in an arid climate, which kind of doesn't make sense biologically, and then a third set of extinctions based upon these biostratigraphic ranges of key taxa. Next. So where I want to take you today is the last places, well, places I've been spending the last 15 years, to Wappetsburg Pass over here in the Eastern Cape, Luttsburg Pass, we'll talk about Tweefontein potentially, and then Batuli in the Free State, where we were a month ago, right back there a month ago. And the way in which these rocks, which are green and red, were correlated across the basin for 200 kilometers was based upon a unique boundary interval that they call a laminated bed, which was a playa lake deposit that got deposited in response to aridification. That aridification resulted in the plants dying out here, the animals relying on those plants dying out, and then being replaced by this Lystrosaurus, and a changeover from these meandering to low sinuosity to braided systems at the top. Okay. So if we take a look at this model very easily, what we'll be looking at is this progressive, supposedly climatic drying, the loss of vertebrates at this point, the presence of this laminated bed that marks the Permian-Triassic boundary that is believed to be coincident with the marine extinction, and then this recovery phase where the red beds represent a change in climate, which I will demonstrate to you has no bearing on climate at all. Okay. So we're going to do 5 things today. 5. Count them. 1, 2, 3, 4. Come on. 5, right? 5 things. We're going to take a look at whether or not these plants, Glossopteris, go extinct at the same time that the vertebrates supposedly turn over, right? Because if the plants go, the animals go, all hell happens. We're going to look at whether or not the vertebrate record is, as interpreted, this really high stratigraphic resolution. Right? Can we track these over several meters of loss? We're going to look at the event bed, which is here. We'll come back to Batuli, and this is across the Orange River at the Caledon location. This event bed that is supposed to be a playa lake deposit and coincident with the PT boundary. We'll look for evidence of aridification and a restructuring of the river systems to these braided systems in what's called the Katberg Formation, and whether or not the turnover is actually coincident with what we see in the marine realm. So we got 5 things to do, right? 5. 1. Right? Glossopteris extinction. So I'm going to take you here to Old Luttsburg Pass in Tweefontein, where we published work from 2005 onwards. We have a paper coming out in GSA Bulletin in the next month or so that's detailed work in Luttsburg Pass. But let's take a look at whether or not these plants actually undergo complete loss at the purported boundary. You'll see photographs in a minute where you're going to go, where are the rocks? Huh? Where are the rocks? Because this landscape hasn't seen rain in any significant amount of precipitation since the Miocene. Okay? So for about the last 23 million years or so, this has been a dry place. And the landscape, because of a dry place, is covered in small shrubs. It's covered in a lot of rubble debris that has weathered out mechanically, not chemically, fallen down from these high escarpments, which are the sandstones and the capping dolerites. The dolerites were intruded as in the late Triassic, early Jurassic, as South Africa spread apart from Antarctica and India. And this place is just littered in crap. So there's not much rock exposure. The rock exposures you'll see are these ridges along the edges and in these erosional gullies that are called dongas. Okay. So Smith and Botha-Brink placed their Permian-Triassic boundary based upon their raw data of vertebrates right about here. And we've published on stratigraphic section going through their PT boundary to here. But in terrestrial systems, unlike marine systems, the amount of lateral variability in rock type is dramatic under short distances. I mean, dramatic. So it's not possible to publish a single stratigraphic column and make it representative of what's there. So in order to do that, we've been developing these stratigraphic frameworks, in this case at Old Lutzeburg Pass, where we have the main section I just showed you, and all of these ancillary sections that are correlated on the basis of walking the top of those sandstone benches. 50 meters, click GPS. 50 meters, click GPS, right? So we've got these datums. I know maybe dating myself and my kids, but how many people played Chutes and Ladders as a kid? Yeah, so you got the concept, right? So you walk over here, you shoot down to another sandstone, you walk the sandstone, correlate that, you go up the ladder to the next sandstone, and you put together this framework, right? So we got a Chutes and Ladders strategy for doing stratigraphy. And you'll notice that this particular stratigraphic section, we also have fossils, where fossils had never been found before. That we've got Glossopteris leaves here and here. We've got pollen here, Glossopteris leaves here, Glossopteris leaves here. But we also have vertebrate skulls. We have Dicynodons here. We have Lystrosaurids here. And Smith and Botha-Brink's boundary is here. I wonder what that could mean. We have beautifully preserved leaves. We published on this in, actually last year, 2017 in Paleos. We published in Geology a couple of years ago. Notice that these very nice leaves with beautiful veination. We've got numerous different morphotypes and horsetails that occur here, 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 and here. Smith and Botha-Brink's PT boundary is here. And right at this point, we've got a half-meter wide petrified stem of a tree. Now wait a minute. The idea is that all those trees and plants die off here. But now we've got a tree that's beautifully preserved, silicified above that. I wonder what that could mean. Right? And this will give you an idea of what the landscape looks like. And you'll notice that the rocks are only here in these dongas. Okay? Plus, we've got the pollen. Now, because of the doleritic intrusions that happened in the late Triassic to early Jurassic, much of this rock is cooked. What do you mean by cooked? Well, temperatures high enough to bring slight metamorphic grade to some of the rocks close to intrusions. And you'll notice in the case of these pollen grains, they really look like shit. Right? No, they do. They're not great. They're not well preserved. They have enough features on them that we can identify them. And Cindy has been expert at being able to do this. And what we find are that we have the typical Glossopteris pollen that you would expect. But we also have the groups of seed-bearing plants, the conifers, called peltosperms and Charistosperm, that the model says comes in after the extinction. That this is the recovery flora. No, the recovery flora was there with the with the glossopterids. They were just outside the taphonomic window, not getting preserved because they weren't in conditions to have those leaves preserved. So we've got this mix that is all late Permian, not just shortly above the supposed boundary, but into the Lystrosaurus zone too. So biostratigraphically, it's telling us we're in the late Permian and not necessarily in the Triassic. Right? Two. Everybody with me? Two? We only got 3 to go. I know some of you are going like, when is this going to be over? The second thing is this idea that we can identify a mappable unit of these interlaminated beds across the basin. This is what the laminated beds look like at this locality. Unfortunately, that locality is about 60 meters above the PT boundary at that site. Who would have guessed? Because that's the site where the PT boundary is supposed to be, according to publications before 2014, which puts it here. But the other thing that we've been able to find, we'll come back to, is that we've got porcellanites. We've got volcanic ash layers that we hadn't seen before. So let's take a look at the reliability of the vertebrate data before we take a look at hard chronometric data. So all these little holes that you see are where we have drill core for paleomag. Right now we have over 2 kilometers of measured section. We have about 2,500 drill cores for paleomag, and all of our sections have a very high resolution on this. And Roger Smith and Jennifer Botha, after a long and drawn out fight, finally gave us their data set with their GPS coordinates. Right. We can talk about that over a beer, because that's a story unto itself. So we were able to take their GPS coordinates, identify the sites where they collected the vertebrates, and put them into our stratigraphy, right? Because that should all make sense. Right? Particularly if they say, these are only 5 meters below, these are 10 meters below, this is 20 meters above, right? And this is where they place the boundary. These are our Glossopteris leaves, which we now know are in the Lystrosaurus zone. Right? Yeah. So in addition to the leaves, we also found new vertebrate skulls, one of a latest Permian, supposedly in the Triassic, that is of a, should be extinct. And we found the characteristic Lystrosaurus murray, which is supposed to be Triassic. So we know that we're at the boundary, right? And we moved the boundary actually up into this horizon in 2015. So we've got our skull here, we've got our skulls here. If we were to put the boundary between the 2 biozones, we would move it up to here. Smith and Botha, wait a minute, huh? Where is Smith and Botha-Brink's boundary? If we use their raw data for the vertebrates that say this one is 27 meters below, and this one is 57 meters below, what principle of Steno's stratigraphy are we violating? This is a test. It won't be graded. This is a test. So this one is 32 meters below. That one's 57 meters below. Anybody? Do I have to call on somebody? Come on.
That's a super question, Bob.
Thanks, Chuck.
You're cozy.
So what would you say? Oh, there's an overturned section, right? There's a fault, there's got to be an overturn. No, there's no fault. And if we take the raw data and the GPS positions into our sections and determine the position of their Permian-Triassic boundary, oh, it could be here, or it could be here, or it could be here, or it could be here over a span of almost 100 meters. So what's the credibility of that data set? You know, when some of us in this room was in college, and I won't point names or name Chuck, when some of us were in college and computers first came out, there was this idea of GIGO. Anybody ever heard of GIGO? Garbage in, garbage out. Whatever you've pumped in a computer, if it's not right, you're going to get an answer. But if it's garbage in, it's garbage out. Which would imply that the biostratigraphic positions of the samples used for this model might not be as reliable as one might think from the literature. Hence, we come back to Ronald Reagan, trust but verify. Right? Let's go to 3. I know, 2 more to go after this, 3. Right? This idea of the laminate bed. Let's go to the Orange Free State where we were last month. And this interval is supposed to be the event bed. This is supposed to be the last paleosol before the event bed with all these nice big nodules. And what's gorgeous about the Betuli locality and the Fairydale farm locality is that specimens like this lie at the surface. Just, well, they were there. Okay? Just beautiful, complete skeletal materials, which is very impressive and makes it easy to put them in a stratigraphic position. About 10 years ago, I know, 10 years ago, that ages me, 10 years ago, we tracked this laminated unit, this unit right here, it's my colleague Johan, across the Bethel farm from one side of the mountain to the other side of the mountain, because if it's a mappable unit over an area of about 1 kilometer, shouldn't you be able to walk it? It's like walking across campus. If it's a horizon that is consistent and mappable, you should be able to walk entirely across campus. And what we found was the model that was proposed by Peter Ward and all was that this boundary of laminated unit was contemporaneous. And what we found was that from one side of the hill to the other side, there was about 8 meters of separation between the two. Now, if you were a consultant or a contract for work and you brought this to the guy who was paying you, what do you think he would say? I want to know if this is a consistent horizon. And what would, yeah, you'd probably say, this is not consistent horizon. I'm not going to target that. And indeed, even though we've demonstrated this almost 10 years ago, this is still the criterion on which other vertebrate South African workers use to go, oh, we're at the PT boundary. We saw this facies rather than this boundary. Okay. So let's go to the PT boundary right here. Yeah. And this laminated mud rock sequence is supposed to be, well, you can read it, right? It's these couplets, silt, mud, silt, mud, silt, mud, silt, mud, sand, silt, mud couplets that are distinctive. See figure 2 of ours. Figure 2, right there. Okay. Keep that in mind. Keep that in mind. Figure 2. Everybody got that figure? Captured it? Does anybody need to take a selfie with it or a photograph? Yeah. Okay. So we're going to go to this location. This is their image. This is the PT boundary according to them. And they say that this boundary, mappable unit, which we just demonstrated is not, is the result of climatic disaster and a playa lake deposit. So if you get into this game, one of the things that you want to do when you make a claim is to substantiate that claim. Right? So up until last year when we published this paper, nobody had ever shown a thin section. Why show a thin section? Because I say it's a laminated bed. And if we look at, next, there we go. If we look at this bed, and here are 2 of my students at the bed right here. This is their photograph. This is our panorama. If we look at the bed at this point, where the boundary is supposed to be, it conforms to the reddish interlaminated, quote, unit. 180 meters away, oh, it's green. Huh? How can we go 180 meters from a reddish bed that's supposed to be playa lake deposit into a greenish bed that's homogeneous and has no structure or primary structures at all? But the bed itself doesn't have any primary structure. So these are the first thin sections. We published that Actually, it's coming out this year. It was online last year. And you'll notice that most of these sections look to be homogenized, pedogenically altered. There's some bits and mud chip fragments throughout this interval. The PT boundary is right here, right there. And you'll notice that it changes from one side to the other. Analyzing the red beds and the green beds chemically shows no geochemical change in signature. Nothing different. And we have analyses for all major and minor and rare earth elements, and there's no difference between the greens and the reds. No idea of aridification. There's no calcium buildup. There's no gypsum. There are no desiccation cracks. There's nothing to demonstrate there's aridity. And you'll notice there's nothing to demonstrate interlaminated units. Right? There's no bedding here. Right? And the question then comes to, is that red color a function of climate, as is claimed? Now, the only way that you can get any handle on the proportion of Fe2 to Fe3 is either to do a titration, which is a real pain in the butt and not very good, or to use Mossbauer spectroscopy. So Darby Dyer, who's a planetary geologist at Amherst College, she's about the only person in the Northeast who has Mossbauer. She ran these analyses for us. And what you can see here, the only difference between the greens and the reds is that the total amount of Fe3 in the reds is due to fine-grained hematite. Now, I don't have enough time today to talk to you about why it's fine-grained hematite. We have a model out there for how this works, and we know that that fine-grained hematite adheres to clays. It's not anything but clays, and surfaces clays. So we've got a model to describe that. But this idea of aridification from green to red, here's 5 and 6, right next to each other, right next to each other. 5 meters apart. Was it arid over here? Was it not arid over there? It's a climate signal. It's got to be arid everywhere. Right? So we have no evidence for aridification whatsoever, and we have no evidence for Playa Lake, and we have no evidence for this interlaminated unit, but it's still the gold standard in South Africa for identifying the PT boundary. Next. And if we go even a little further, we did in 2009, you can see that we now run into this interlaminated unit at about 400 meters away, and we've got good ripple marks, we've got good bioturbation, surface trails, we have some wrinkle structures, we have burrowing structures. We have a typical fluvial abandoned channel set of deposits. Nothing special, nothing unique, and they occur throughout the sections. So, number 3, no laminated bed. Number 2, maybe these distributions aren't all they're cracked up to be, and maybe 1, we don't lose plants here. Okay. 4, we're getting there, we're getting there. So the idea is that as aridification occurs and we change over to this catastrophic climatic change, we change the river systems from meandering to low sinuosity to braided channels. And those braided channels are in the Katberg Formation, which form all of these capping sandstones. So we're going to go to Old Wappetsburg Pass, and here's where I hope things work, because we're going to look at whether or not these geometries reflect braided channels. So the Katberg Formation occurs high on the outcrops. This is the capping dolerite intrusions. Katberg is here. And as you can see, it's at the top of a damn mountain, right? How do you characterize outcrop at the top of a mountain? On tippy toes, right? So you kind of stand on the edge of this steep gradient, and your face is here in the sandstone, and you're hoping you don't fall down. Right? There's no way to actually characterize that because you can't see laterally. You can take photographs like this from a distance, but again, you're not orthogonal to that sandstone. You got to be at 90 degrees to see things. So what I'm going to take you on is a little drone ride, because we've been incorporating drones for the last number of years, that we can track these paths, tie them into our stratigraphy, and get an idea of what the architectures are like. Okay, so here we go. How do you land a drone in the middle of a rocky field? Let's see if this is going to work. Come on. Come on. Don't go black on me. Oh, damn. I think it's going to go black on me. It's not going to work. Okay. So we've been incorporating drones to take images of of our areas. This is Tim Stonecipher from Colby's IT department. And what we're able to do is to run 2 hours of imagery, bring that imagery back to the truck in the field, download that imagery, and come up with a 3D model within an hour. It's pretty incredible. And that 3D imagery, which if we can get that next thing to work, I'll show you, that 3D imagery now allows you to see the architecture of those fluvial deposits from a distance to up close to high resolution, depending upon the baud rate that you're doing. I was going to bring this model, but when I was running it on, what's today? Today is Thursday, we're running it on Monday. It was a 3.8 gigabyte model. And I didn't think that that would be easy to show, right? So if we go to the next thing, please. Oh, come on. Click on Tools for additional features. That's what I was afraid of. Yeah, it's not going to go. Okay, so imagine for a second. Imagine for a second. So we've got this 3D model, and some of the faculty may know this. Agisoft, which is a Russian company, offers a modeling program called PhotoScan for $59 for an educational license. 59 bucks. What a deal. Of course, the Russians now know everything on the server. No, they're our friends. They're not even going to think about hacking our servers, are they? With a little worm inside PhotoScan. No, we trust them. Maybe. So what PhotoScan allows you to do is to develop these models, export them as PDFs, and then that PDF is rotatable. You can zoom in, you can zoom out, you can rotate, and I can show you afterwards on my computer if those of you are interested. Rotate this model, and in a day in the field, you can go, I need to get more information here. I don't have to come back to the States to do this. I can do this right in the hotel at night. And it's a fascinating way to do sedimentology because now you can plan from day to day to day to day. Right? You're no longer relying on photographs. Right? You're relying now on 3D models. And now we've 3D modeled most of our areas in the Free State. Sorry, it didn't work. Okay, so that was 4. And what I can tell you, if I could show you the model and rotated it, that sandstone body at the top is 30 meters deep, thick, 30 meters. It's highly constrained to about 400 meters, and no braid plane in the world. Braid plane, high sediment load, low water, is 30 meters deep and 400 meters wide. And I could go through other data to tell you why we don't believe there's any braid planes there. That's 4. Number 5, timing, timing, timing. Timing is everything, and I'll be done shortly. Thank you for your attention. We'll go back to Old Lutzeburg Pass. Right. In 2015, we published a ID TIMS, a chemical abrasion ID TIMS date from a small horizon. These are the zircons, and this is below the vertebrate zone transition of an early Chancetian age. Now, remember that the PT boundary is 252.9. This is now 253.5. And this is only about 60 meters below, quote, the boundary. The paper that we have coming out next week, 2 weeks or so, we now have more zircon-bearing beds in the same stratigraphic framework. That these zircon-bearing beds are all detrital zircons. This is a ashfall, right, a sedimentary deposit. And these dates are a little different than the ashfall date. Oh, that's right, got this. And maybe I should just hear. And this ashfall date is Wu Chao Pingian. What? It's an older date above a younger date, which can only mean one thing, right? We made a mistake. No, we didn't make a mistake. Can only mean that those have been reworked in this closed basin. Remember, I told you it's a closed basin. Everything just comes out of the mountains. So you get reworking of the landscape. The big problem with terrestrial sections is they're always eroding and always depositing, always eroding, always depositing. And this tells us that we've got reworked Wuchao-Pingian. So we've got a good ashfall date here. That's early Chansingian, Wuchao-Pingian above it. But how much time is actually represented? That's where John comes in, because we got Paleomag. So when John does his drilling at any competent bed of rock, we take anywhere from 10 to 14 drill cores, because as Bill can tell you, repetition, repetition, repetition of data gives you the best data set. Of course, there are individuals who have published on this before who thought the perfect data set is n equals 1, right? Because n equals 1, you've got it all, right? Nobody can argue because it's one date or one analysis. And the one thing that we published 2 years ago was the presence, I'm out of batteries here, almost. The presence of this reverse zone right above our porcelainite with this early Chansingian age. So we got a normal polarity chron, a very small polarity chron that occurs right here below an erosional contact with a sandstone. And then a normal polarity chron that continues up. The paper that we have coming out in GSA Bulletin, we now have another polarity chron. Another cryptic reverse polarity chron. And let me just walk you through the stratigraphy. So this is the one I just talked about. This is Smith and Botha-Brink's boundary. This is a sandstone that we use as a datum where we have Glossopteris beneath it. We've got skulls in here. The wood comes from here. And if we walk only 50 meters to the next donga, that sandstone looks like this. That it has analog, that it has a erosional boundary of sand next to a coarse siltstone that comes back up, is then cut by another sandstone body. And the only exposure of the siltstone, of the floodplain deposits we have, are about 8 meters worth here and about 8 meters worth here. Everything else is covered. And we've drilled this now 3 times. So I think we're pretty confident that that signature, and you see some of the holes right here, that this signature is a reversal, a cryptic reversal. And if you didn't drill at high resolution in the stratigraphy, you would miss it. If you only drilled every 5 meters or so instead of every competent bed, you would miss it because it's been eroded out. Hence this idea of time has to be resolved also with magnetics and not just ash falls, right? Because the magnetics give you this higher resolution, which now means that when we compare it to the published stratigraphy or the magnetostratigraphy from the same location, I want to emphasize that these data are the same location data as ours, but we can't replicate theirs. That supposedly at the PT boundary, it's in a normal zone, it's underlain by a short reversal, overlain by a reversal, and that the Lystrosaurus zone is this big, long, normal polarity with very many gaps in the sampling. So if we put the ash, the dates, in the polarity stratigraphy, what we find is that right here are syn sedimentary zircons at 253.5 coordinate at this point in the magnetostratigraphy, Chansingian. We have Wuchao-Pingian zircons that are about 257 reworked just above the porcelainite. A little bit of time missing here. And we now have another normal chron overlain by a short reversal chron which tells us that we're in this part of the chrono and magnetostratigraphic record, which is almost 1.5 million years before the event in the marine realm. 1.5 million years is a long amount of time. To go plus or minus 1.5 million years will make it equivalent. Right? So our contention is that this Daptocephalus to Lystrosaurus zone is not equivalent to the marine extinction event. Why is this important? Oh, okay, so in conclusion, 1, 2, 3, 4, 5, we'll go back here again, right? No vegetational collapse, unreliable raw data, no event bed, no geochemical evidence for verification. Katberg is low sinuosity, and chronometric and magnetostratigraphic data tell us we're in the latest Permian and not in the Triassic. If I were a lawyer, I'd rest my case. But the debate goes on. And why does the debate go on? The debate goes on because of this. If the Permian-Triassic extinction is a model for how ecosystems are going to respond in the future to a unidirectional change in climate of increasing temperature, and we published carbon dioxide PCO2 estimates from these rocks 4 years ago now, and the PCO2 estimates from the soils that formed in atmospheric equilibrium to PCO2 tell us we're anywhere from about 550 parts per million to potentially 1,700 million parts. It's the model's uncertainty. So if we continue in a unidirectional way of increasing carbon dioxide in the atmosphere, and we know what the reaction is of biological systems to increasing temperature, our models better be right. Because if the current model of marine and terrestrial ecosystem collapse at the same time, we are in a hell of a lot of problems. Right? We're in deep shit, right? If they both go together. If they are not, if they're diachronous, right, then why are they diachronous? Right? Can we use the Permian-Triassic model? And because we don't believe that the South African record tells us that information, that's why we're going to China starting this June for a 3-year project in the Bogda Mountains in these rift systems, which are fully continental, where we do have radiometric dates that span both the latest Permian and the earliest Triassic to see what the response of the terrestrial ecosystem is. Because I live on land. I don't live in the ocean. And I want to know what happens in the case of catastrophic Earth system collapse. So I'd like to thank all of my colleagues, all the funding that we've had over the years from NSF, and all the students that have worked with me over time and have done honors theses and have been co-authors on publications, because you know, undergraduates can do research, they can do quality research, and there's no reason to become a scientist late in life. Get started early. I'll come back to the States.